Hi guys, in this tutorial we'll demonstrate yet again another way of another example. We have another example where we determine the moment of inertia about an axis. For this question we're going to look at two methods where in each case we're determining the moment of inertia about the x-axis, but in one method we'll go directly, we'll see why that works, and in the second method we'll choose a method which will actually now require us to use the parallel axis theorem. So we can look at this example as an extended example on the parallel axis theorem and how to use it. Now, how do we proceed? Well, to work out this question, or perhaps what they're saying here, we are finding the moment of inertia for the shaded region about the given axis, about the x-axis that is. Now to do that, like I mentioned, we have two methods. In the first method, we'll pick a section that is horizontal. So pick a differential section that runs from here in this way, coming down all the way up to there. So we'll pick a rectangular section like that. They just color this so that it stands out. So this is the section that we have selected. And just like in the other cases, including like on the method of dealing with centroids, we'll try to make sure that we utilize this point here along that boundary whose equation is given, so that we can utilize the coordinates of that point in terms of x and y. Because for this point, this part can be seen as the x value. So up to here, this is x. And up to there, we can take this as y. So for this point, the points of the variable x and y will be related by that expression there. Now, what does choosing a differential section like this imply? Well, firstly, to find the moment of inertia about the x-axis, what we need is the integral. We've already seen this. It's the integral of the distance squared multiplying dA, the differential area there. But the property of this distance d, it has to be the distance from the axis we are considering, in this case the x-axis, to the differential section that we have selected. Now the concept here is that this distance has to be uniform. It has to be a constant distance. All the points along that differential area must be positioned the same distance from that axis. In this case, we see that this actually holds. All the points along that differential section are located exactly the same distance d from that section to that axis. But in this case, when you look at this distance, observe that this distance is actually just in line, or it is the same as what? Look at that. This distance d is actually the same as the y value there. So instead of using d squared there, we end up using just y squared. So here, our distance d can be seen to be equivalent to that variable y. So here we end up with y squared dA. Having sorted out that, the next thing we want to sort out is this differential area dA. We have selected a section that is rectangular like this and horizontal. Its thickness here, if you observe going back this side, the thickness here is in terms of the y-axis. So this can be taken as dy. The next thing, we want to now determine what the width here is going to be. But we want it to be as much related to that variable x as possible, either x or y, so that we can use that, that equation for that point x comma y, the equation for that curve there, to relate them should we need to. Now, how do we do this? Well, we observe that all the way from here up to there, this part is given as 100 millimeters, but we selected this point there to be x, which ensures that up to this point, this part is just x. But guess what? If you were to subtract x from this 100 meters, what you'd get is this section that we are actually interested in. In other words, the width of this section can be seen as just 100 millimeters less that variable x. So in other words, our differential section dA can now be evaluated as 100 less x there, then multiplying that thickness dy. So therefore, the moment of inertia about the x-axis will now just be equal to the integral of y squared. Then we have that 100 minus x here. Then we have dy. Okay, sorry for that. At this point, we can now distribute that y and the dy so that we end up with two integrals. For the first part, the 100 can come out. So now we only have y squared dy. Then minus the y squared now goes to the second term. We now have y squared and x here, then dy. So these are the two integrals that we now have to evaluate here. So the first one can be evaluated, but we'll hold on for now. But now for the second one, we see that x here is also a variable. X can be related to what y is. In fact, the fact that we selected x to lie along that curve, and that is where y also is, the values of x and y are connected along that line by this equation. So let's take advantage of that to find what x is in terms of y. If we use this relationship, what do we see? We see that we can express x as a function of y, and this is going to be y squared over 400. We can now get this and plug it where we have x here. And what are we going to end up? So we'll just copy this. And where we have x there, we're going to plug in what x is in terms of y. So in this case, where we have x there, we'll erase x. And instead of x, we'll now substitute y squared over 400. Notice that if we now simplify that expression, we now have 100, the integral of y squared dy, minus, this now becomes, the 400 comes out, we now have 1 over 400, and this becomes the integral of y to the power 4 dy. This is not dx, that is dy. I wrote dx at some point. Yeah, this is dy here, not dx. So note that this is the same dy that was distributed, not dx. Sorry for that. I hope you guys were able to pick up on that. Okay, once this is done, we now just have to set those limits, the limits of integration, then integrate so that we have a final solution. Now, since we are integrating this with respect to y, this is with respect to y, we have to just go back to the graph and identify the smallest value of y and the biggest value of y. The smallest value of y is at 0, and the biggest value of y according to this is at 200 there. So we're integrating from 0 to 200. So this is 0 to 200. Also here, this is from y is equals to 0 to y is equals to 200. Based on that, the integral, this is 100. This would be y to the power 3 over 3 from 0 to 200 minus 1 over 400. And then again, when we integrate this, this is now y to the power 5 over 5. Again, the limits of integration, 0 to 200. So when y is 0, the whole thing just gives us zeros. So we'll only play with when y is actually 200. So when y is 200, look at what we get here. This is 200 to the power 3 over 3 minus 1 over 4. And then here, when y is 200 again, this is now 200 to the power 5. And this is over 5. Now you simplify this. This will reduce to something very, very big. So this is going to be 107 by 10 to the power 6. And don't forget the units. We were using millimeters. Those distances were in millimeters. So this is millimeter to the power 4. So this becomes the moment of inertia about the x-axis using that method. Now let's look at the second method. Now, in the second method, what we're going to do is we're now going to choose a vertical cross section. So we're going to choose a section that runs like this. Now we want to use this section to determine the moment of inertia about the x-axis still. Even for this one, we strategically select this point and ensure that this point is running along that boundary, so that this point can still be taken as x comma y. Now selecting this ensures that here we have y there, will become useful later on, and we can pick a variable at the bottom here, and that variable can be taken as x there. Now how does it work here? So to determine the moment of inertia about the x-axis here, it's a little bit tricky. You see, in that evaluation of the moment of inertia about the x-axis, where we have the integral of the distance squared multiplying dA. See, this distance here, when a section here has been selected like this one, the distance d has to be a distance that is uniform, the same to the section, to every point on our selected section. Of course, the selected section is assumed to be very thin, so that in the previous case we saw to say if this is the section, then the distance d from the x-axis was taken as the same distance to every part on that section. And this of course was highlighted by the fact that we could see that description. But in this case, however, we do not get that. What do I mean? For pieces which are nearest to the end, we see that distance will just be something small. For sections which are slightly further, we see that the distance d will be slightly more. And for sections which are even further away, for the piece of part of the section further away, we see that the distance is going to be more, and so on and so forth. What does this imply? The distance d is not constant from the x-axis to the section. Different parts of the section will have a different distance. Because of this, we cannot use this method. Then what works here? Well, in this case, we must then resort to using the parallel axis theorem. How does it work, and how do we use it? Well, in this case, we start with one fact, one simple concept. See, for a rectangular block like this one, we saw in the previous video that the moment of inertia about the, let's say, the horizontal axis, let me not say about the horizontal axis, yes, about the horizontal axis, that is passing about through that centroid, through the centroid of this section. We saw that the moment of inertia here, this was given by the moment of inertia about, let's set this to be the x prime axis. So let's say this is the x prime axis. We saw to say that this moment of inertia was determined by 1 over 12, and then here we had bh to the power 3, where h was the height from here all the way up to the edge there, and b was the thickness from here to here. We saw this in the previous video. We did make that derivation. Okay, so we saw that. But this is not the full thing that we are looking at. This rectangle is actually just a piece, meaning this is the differential section, such that firstly, it's a differential moment of inertia about the x prime axis. And apart from that, of course, this is still 1 over 12. But the b here, it's not the breadth of the whole thing. It's the breadth of the differential section selected. And this section is in terms of the x-axis. So because of that, this is dx. So the breadth is actually just dx. And the last thing here is the height here is not h. Of course, in this derivation, that height was h. But notice that in this case, for this section we have selected, the height is actually y. And the height was raised to power 3. So here we have y to the power 3. What is this? We have the moment of inertia, the differential moment of inertia, or let's say the moment of inertia of that differential section we have selected. This has turned out to be equal to 1 over 12 multiplying y to the power 3 and then dx there. So this is what we have. Now again, the parallel axis theorem came out to be if we have the moment of inertia about the centroidal axis x prime, then we could use this to determine the moment of inertia about an axis at the bottom here parallel to that x prime axis, provided we knew the distance between the two axes. So we ended up with, if this is the x-axis, then the moment of inertia about the x-axis was just equal to the moment of inertia about the centroidal axis x prime plus, then we had the area A multiplied by the square of the distance between them. The distance between them being that one there. Of course, it had to be perpendicular to both axes. So this is what we have. But observe that what we are actually using is not the parallel axis for the whole structure. We are going for the differential section. So we are using the parallel axis theorem to find the total moment of inertia or the moment of inertia of a differential section about the bottom. Then we will have to perform an integration to transform this into getting the moment of inertia for the entire structure. What do I mean? We use the parallel axis theorem on this structure so that we end up in this position. But after reaching this position, we then take note of one thing. This is not the total moment of inertia about the x-axis. It is in fact the moment of inertia of a differential section selected, this rectangular differential section. Doing that, what does it imply? It means that even this one, the moment of inertia about the centroidal axis, it was actually a differential moment of inertia. What does that change? It changes one fact here, or one part. It now implies that when we were looking at the area here in this expression, this is not the total area of the structure, but instead it is the total area for the differential section. So we write dA to mean the area of the differential section. I hope you guys followed that. Note that this is the parallel axis theorem, but applied to a differential section. Now, the last thing that we have to observe here is the distance between the two structures here, the distance between the two axes now, the centroidal axis and the x-axis we're going for. Notice that distance now, if we go back to this structure, if for the rectangle here we set the midpoint to be here, then the distance between the centroidal axis for that selected section, notice that distance is actually just the distance from the x-axis to the centroid of that section. And the distance to the centroid of a section, remember, that was taken as y tilde, because this is in terms of the y-axis. Because of that, we can actually present this as dix is equals to dix prime plus dA, the area of the differential section, then multiplying y tilde squared. Now, we have already seen what the differential moment of inertia about the centroidal axis is. We derived that and we saw that it will be given by this expression. So we can bring that, we can get this, copy it, and we'll substitute it in this expression. So we now have the differential moment of inertia of that rectangular section, where we have that moment of inertia about the centroidal axis. We'll put this expression. The only thing that we now have to sort out is what the y tilde is and what the differential area dA there is. Now, having done this, let's determine what that centroidal or that differential area is. For this differential area, what are we looking at? So for the differential area, we need one, the height of the differential area. Well, according to this, the height there is just from here all the way up to there, and us having selected that point to be x, y, ensures that the vertical part is basically just y there. While the base here, which is just the thickness, it is in terms of the x-axis, I mean. So this can be taken as dx, so that we can then calculate the area for the differential section there, dA can now be seen as y multiplying dx. So this becomes what replaces that dA there. So what are we now seeing? We now have dix is equals to 1 over 12 y cubic dx plus y tilde squared. And then where we have dA, we're now plugging in y dx. The only thing left is now y tilde squared there. So y tilde squared, what are we seeing there? Well, for y tilde there, where is it? Y tilde is only up to the centroid of that rectangle, but the whole length of the rectangle is y. So we can also relate y tilde to y. So if the whole length up to the end there is y, then y tilde, which only comes up to the center of this rectangle, can be related to the full length y, in the sense that y tilde has to be y over 2. I hope you guys remember this from centroids. So what does that imply? It implies that this structure, where we have y tilde, we now have to put y over 2, but just squared. So we'll have this is now y over 2, and we will square this. Let's write this better. So I have this, and we'll square that part. So now we have this expression. So all we have to do here is, if we wanted to find the moment of inertia about the x-axis, we now have to evaluate the integrals. So this is this part will get the integral, and plus the second part, when we square that part, this is going to be the integral, y squared there, then the y squared will multiply the y there, giving us y cubic. And then the 2 gets squared, giving us a 4. Then we have dx. So that what we have is 1 over 12, the integral of y cubic dx, plus this becomes 1 over 4, then the integral of y cubic again, then dx. But we have a challenge here. This is y cubic, but we're integrating with respect to dx. This won't cut it. We have to change this to in terms of x. Well, luckily for us, we selected the point x comma y there, such that it lie on that line. In that line, we so to say the values of y are connected to the values of x by that equation. So we then get that. We'll use it to transform our y cubic there. So this implies, or from here, we can say y is equals to 400 x, but just the square root. We know to say the square root just implies we can square root that 400 if we so wish, so that it comes out of the of that square root. In fact, let's do this. If we square root the 400, because we know this can be written as the square root of 400 multiplying the square root of x, then we'll square root the 400 so that we get the square root of 400 is 20, and then leaving us with only the square root of x, which can be written as a fraction. Now, when we get y to the power 3 there, but now we know what y is, so we'll just copy this, and where there is y, we'll just substitute. So where we have y, now we make the substitution. This is now 1 over 12. The integral of y cubic. Y is coming with that, so this becomes 20, and then x to the power 1 over 2, but this is raised to power 3. Then dx. Plus, again, we have 1 over 4. Again, y cubic here, so this is the integral of 20, x to the power half, and then again, this is to the power 3 dx. So this is what we're seeing, this is what we're simplifying. 20 to the power 3 can come out, so here we're going to have 20 to the power 3 over 12, but now we'll remain with x to the power 3 over 2. So I have distributed the 3 to 20. So this is 20 to the power 3, and this is x 1 over 2 to the power 3, which reduced to just x to the power 3 over 2 dx. Then plus, in the same way here, I'll distribute that 3, the power, so that I will have 20 to the power 3 here over 4, then the integral of x to the power 3 over 2 dx. Having done this, we now want to fix in. Don't get tempted to divide this before you evaluate those powers. So first you have to evaluate those powers before you finalize this. But the next thing that you'd have to do before doing that is fixing the limits of integration. So if you go back to our diagram, we're integrating with respect to x. The smallest value of x is 0. The maximum at this point is 100 millimeters. So it's from 0 to 100. So we have from 0 to 100 here, from 0 to 100 there. So these are the integrals that you now have to evaluate. So all you have to do is integrate and simplify. So you guys can try to evaluate this and try to see if you'll be able to perform the integral just fine, substitute the limits, simplify the expression, but you should be able to find 107 by 10 to the power 6 millimeters to the power 4, even in this case. So there we have it. Two methods. In one method, we were able to work out the question, find the moment about an axis, just directly. In the second method, we explained why it was not possible to take the direct approach, and we demonstrated another scenario where the parallel axis theorem can be put to good use. So I hope you guys found this helpful. If you'd want to see more tutorials on moment of inertia, please share the video, like it, let me know in the comment section as well. Alright guys, hope you found this helpful. See you in the next tutorial.